So this video will go over section 7.4. This first slide is on from section 7.3, but we do not cover section 7.3. So there are a lot of different gas laws, and we will only focus on the ideal gas law that is comprising all other laws into one. And so whenever we talk about gases, we need to specify a lot of different variables, because gases are very different from solids and liquids in the fact that they are, you can compress them, you can expand their volume, they depend on temperature. The container they're in will experience different kind of pressure depending on the volume and the number of moles. So whenever we talk about gases, we need to specify a set of variables that are listed in this table. So pressure, we already saw that in the previous video. The symbol is capital P. Units are atmosphere, millimeter of mercury, torr, psi, and pascals. And as a reminder, pressure is a measure of the number and the force of collisions between gas particles and the container walls. So the more particles hit a wall, and the higher the pressure. Volume, capital V is the symbol. The unit is liters. And the size of the container that the gas occupies is its volume. Temperature, capital T, expressed in Kelvin. The temperature is proportional to the average kinetic energy of the gas particles. So this is something you need to remember. Particles are moving, and it's their kinetic energy that tells you, how much energy they have to move. And it's related to temperature. The higher the temperature, and the faster the particles will move, because the more they have kinetic energy to do it. The number of moles, N, expressed in units of moles, and that represents the amount of gas particles. So often amounts of gas are compared at a set of standard conditions of temperature and pressure, abbreviated as STP, because depending on the conditions, the gas properties can vary so much that to be able to compare them, there has been a set of standard conditions of temperature and pressure. And to say that quickly, we abbreviate this as STP for standard temperature and pressure. The STP conditions are 1 atmosphere for pressure, or 760 millimeters of mercury. And temperature is 273 Kelvin, which is the 0 degrees Celsius. And so at STP, 1 mole of any gas has a volume of 22.4 liters. And this 22.4 liters, this volume is called the standard molar volume, because it's always true no matter what kind of gas you have. If you have a temperature of 0 degrees Celsius, an atmosphere of 1 atmosphere, a pressure of 1 atmosphere, and you are trapping 1 mole of any gas, the volume occupied by that gas will be 22.4 liters. And it doesn't matter the kind of gas. So this is called the standard volume. The standard molar volume, because it's the molar volume at the standard conditions. And so to really understand what this means, there is this illustration of 2 balloons filled with 2 different gases. One is filled with 1 mole of nitrogen, the other is filled with 1 mole of helium. And so they both occupy 22.4 liters, right? The volume of the 2 balloons is 22.4 liters, because you have 1 mole of gas in each. And so they will occupy the same volume, and they will have the same number of particles, which is the Avogadro number, because in 1 mole, we have 6.022 10 to the 23rd particles. So both balloons have the same amount of particles. However, the mass is different because for 1 mole of nitrogen, you have 28 grams of nitrogen, and for 1 mole of helium, you have only 4 grams of helium. So it's the only difference here is the identity of the gas will change the mass, but otherwise 1 mole of course means the same number of particles and the volume will be the same. This is true only at STP, right? This molar volume is only true at standard temperature and pressure. So let's use this molar volume. You probably noticed how this is an equality that says 1 mole is equal to 22.4 liters at STP. And so, as you know, any equality can be used as a conversion factor. So we'll practice using that. And with this problem, how many moles of H2, it's hydrogen, are in 1.24 liters of hydrogen at STP? So according to the text, the given amount is 1.24 liters. That's the volume, right? Liters are a unit of volume. It says it's at STP. So that means pressure is 1 atmosphere and temperature is 273 Kelvin. But really what you want to remember here is that it's at STP. So that means you will be able to use the molar volume as a conversion factor. And what is needed, what the question is asking for is how many moles of hydrogen there is in 1.24 liters of hydrogen. And so here we see we have a volume and we want to know the number of moles. And the molar volume is relating moles to liters. So that's what we will need. We're starting with liters of hydrogen. We want moles of hydrogen. So we want to use the molar volume that says 1 mole of hydrogen is equal to 22.4 liters at STP. And we know we can use this equality because we are at STP. So knowing that we start with an amount of a volume of liters, you want to have the liters of the equality here in the denominator when you write the conversion factor from that. So you want 22.4 liters in the denominator and 1 mole on the numerator. And this way you will cancel the starting unit and get a number of moles, which is what you want. So when you set up the whole calculation, it looks like this. You start with the given amount of 1.24 liters of hydrogen. You multiply by the conversion factor that is obtained from the molar volume. That says 1 mole of hydrogen is equal to 22.4 liters of hydrogen. And you write it such that the liters cancel. Liters of hydrogen cancel. And we're left with moles of hydrogen. So in the calculator, you do 1.24 divided by 22.4. And the calculator answer is 0.05535, etc. Here we want to keep 3 sig figs because the given amount has 3 sig figs and the 22.4 also has 3 sig figs. Remember how the 1 mole is exact and not limiting the number of sig figs. So we want to keep 3 sig figs, and that's why we run to 0.0553. What comes after the 3 is a 5, so you need to round up, and the 3 will become a 4. So the answer is 0.0554 moles of hydrogen in 1.24 liters. So you can use the molar volume to find volume at STP. So let's look at this other example. And the problem is saying, what is the volume in liters of 64 grams of oxygen gas at STP? So the key word here at STP tells you that you should be able to use the molar volume that tells you that you have 22.4 liters of gas when you have 1 mole of gas. However, here the given amount is 64.0 grams of oxygen, right? It's a mass in grams, so it's not moles or liters. And actually the question is asking what is the volume in liters. So we want to find the liters and we have grams. We know that we are at STP, which means we can use the molar volume that says 22.4 liters of gas is, I mean, 1 mole of any gas contains 22.4 liters. So you can use that, but that means you need to change your grams into moles. And we know how to do that. When we want to change grams into moles, we use the molar mass. So then we will go from grams of oxygen, use the molar mass to change that into moles of oxygen. And then using the molar volume, we will change those moles of oxygen to liters of oxygen. So we will need 2 conversion factors. The first conversion factor is the molar mass of oxygen. You know that the molar mass, you get it from the periodic table. So you take your periodic table, look at oxygen. The atomic mass is 16.00 grams for 1 atom, and there is 2 atoms per formula. So you multiply by 2. And the molar mass of oxygen is 1 mole of oxygen equals 32.00 grams of oxygen. And so out of this equality, we can write 2 conversion factors, and they're given here. The next equality is the molar volume. The molar volume says that 1 mole of any gas, so this applies to oxygen here, 1 mole of oxygen equals 22.4 liters of oxygen when you are at STP. And we are at STP, so we can use that equality. Again, there is 2 conversion factors from that equality. So when you are ready to write the full calculation, you will start with your given amount of 64.0 grams of oxygen. And you will multiply by the first conversion factor that will convert your grams into moles. So out of the 2 conversion factors from the molar mass here, you want to choose the conversion factor that will cancel the grams, the given amount of grams. So it's going to be the second conversion factor. The 1 mole of oxygen over 32 grams of oxygen. And we keep the zeros. So this way we cancel grams of oxygen. Next, the second conversion factor needs to cancel the moles of oxygen from the previous conversion factor. So the molar volume will be used such that 1 mole of oxygen is in the denominator and 22.4 liters of oxygen will be in the numerator. This way we can cancel moles of oxygen. And we are left with liters of oxygen, which is the desired unit. So in the calculator, you do 64.0 divided by 32.00 times 22.4. And the calculator answer is 44.8. And it happens to be 3 sig figs, which is what we need because the molar volume here has 3 sig figs. And the given amount has also 3 sig figs, 64.0. The 0 here is significant, so we keep 3 sig figs. The molar mass is not limiting because it's 4 sig figs. So we keep 3 sig figs, and the calculator answer is just 3 sig figs, so we keep it like this. So there is, the volume occupied by 64 grams of oxygen at STP is 44.8 liters.